Hello girls, here in this video I am going to explain you the theorems on prime ideal and maximum ideal definitions. First theorem, R by A is an integral domain if and only if A is prime. Statement, let R be a commutative ring with unity and let A be an ideal of R, then R by A is an integral domain if A is prime. Proof. Now we are in the necessary part. We are considering A is a prime ideal of R and how to prove R by A is an integral domain. Here, since R is a commutative ring with unity element, then we can also write R by A is also commutative ring with unity element. Here what we have to prove, R by A is an integral domain. Means see the definition of integral domain. First property is unity. The next condition is commutative. The third one is no zero divisors property. The first two already R by A is commutative with unity. So the only case we have to prove is no zero divisors. No zero divisors means this condition AB equals to 0, then A equals to 0 or B equals to 0. Now R by A set formation will be in the form of A plus A comma B plus A belongs to R by. The elements will be in the form of A plus A comma B plus A, like that, under addition. Now consider A plus A into B plus A equals to capital A. Now A plus A into B plus A equals to, write A as 0 plus A. Now using the condition of second property, yesterday's theorem, under multiplication we can write this A plus A into B plus A as AB plus A equals to A. Now you see this property, if X plus A equals to A, we are writing X belongs to A. Same this property we are using here. Instead of X, AB is there, so AB belongs to A. Since A is a prime ideal, see the definition of prime ideal. If AB belongs to A, then we can write A belongs to A or B belongs to A. In the same way, A is a prime ideal, so we are taking A belongs to A or B belongs to A. Now using the property of this one, we are writing A plus A equals to A, B plus A equals to A. Now A plus A equals to, write A as 0 plus A and write B plus A as 0 plus A. Now if you take, in the place of this 0 divisors, we are taking A plus A instead of A plus A, instead of B plus A equals to, instead of 0 plus A, then we got A plus A equals to 0 plus A and B plus A equals to 0 plus A. Means what? Compare this one with 0 divisors, it's satisfying under R by A quotient ring. So we can say R by A has no 0 divisors. We have satisfied the three conditions, so we can say R by A is an integral domain. Now second case, sufficient part. Suppose R by A is an integral domain, we have to prove A is a prime ideal. The conditions of prime ideal, you see, AB belongs to A, then A should be belongs to A or B belongs to A. Now for this case, we are taking A comma B belongs to R and AB belongs to A. We are taking from the ideal condition, prime ideal. Now by taking AB belongs to A, we have to prove A belongs to A or B belongs to A. Now here we are taking AB belongs to A. That implies, by using the property of coset, if some element belongs to A, we can write it as AB plus A equals to A. Now using the multiplication condition, AB plus A can be written as A plus A into B plus A equals to 0 plus A. Since R by A is an integral domain, previously we have proved, if it is integral domain, it has a no zero divisors property, that is A plus A equals to 0 plus A or B plus A equals to 0 plus A. A plus A equals to 0 plus A can be written as A. Here B plus A can be written as A. Now by this we can write, using the property, A belongs to A or B belongs to A. Means by taking AB belongs to A, you got A belongs to A, B belongs to A, which means it satisfies the prime ideal condition, so we can say A is a prime ideal. Hence R by A is an integral domain if and only if A is a prime ideal of R. Next theorem, this theorem is also very important. Statement, let R be a commutative ring with unity and let A be an ideal of R, then R by A is an integral domain if and only if A is maximal. Proof, let R be a commutative ring with unity and A is an ideal of R. Since R is a commutative with unity, we can also write R by A is also commutative ring and has unity element. The unity element in R by A will be in the form of 1 plus A. 1 plus A is a unity element for 1 R by A. Now you have to suppose A is a maximal ideal of R, and how to prove R by A is a field. To prove it is a field, already it satisfies the commutative and unity, because R by A is already commutative and unity. The only proof you have to prove is R by A has a multiplicative inverse. For this case, let's take a generator X be the principal ideal of all. Now if it belongs to the R by A, the R by A formation will be like generator X plus A. Any element if you take to the R by A, it will be A plus A, B plus A, like that. So this generator X also you have to take generator X plus A is an ideal of R. Since A is maximal ideal of R, you see this by definition A subset to generator X plus A subset to R. In the definition you have A subset to B subset to R. Instead of B, here A subset to generator X plus A subset to R. Now here generator X plus A subset to R, subset we are taking subset or equals to, so I am taking a equals to generator X plus A equals to R. Now we have 1 belongs to R, such that, see here, this one generator X from the principal ideal, generator X equals to Rx. If generator X plus A equals, the set formation will be Rx plus A. If you have plus A in the right side, we will write in the set form Rx plus A. That's why here generator X plus capital A we are writing here small Rx plus A, and the R belongs to the unity, so I am writing in the place of R as 1. Now consider identity element 1 plus A equals to, what is the one value is Rx plus A plus A. Now Rx plus A, now using the multiplication condition, not addition condition, Rx plus A plus A plus A. Rx plus A and A plus A can be written as A. Rx plus and A plus A can be written as only A. 1 plus A equals to, by using the multiplication condition, you can write R plus A into X plus A. Since R by A is commutative ring, you can write this one R plus A into X plus A in the reverse order. Therefore R plus A into X plus A equals to X plus A into R plus A equals to identity element. You compare this with this one with the inverse property. The inverse of X plus A is R plus A. Therefore R by A has a multiplicative inverse, hence we can say R by A is a field. Now case 2, in the reverse order you have to take R by A is a field and how to prove A is a maximal ideal. Means for this sake, see, to prove a maximal ideal we have two elements A, B and R is a ring. Already we have A, here we are taking B is an ideal of R, such that by taking this condition you have to prove A equals to B or B equals to R, such that we are considering the process A subset to B subset to R. We have to prove A equals to B or B equals to R. For here we are considering A not equals to B. Then some element belongs to B that does not belongs to A. Then the R by A element will be in the form of B plus A belongs to R by A. Now here we took the condition A not equals to B, means it must be equals to B equals to R. This condition we have to prove B equals to R. Since R by A is a field, it has a multiplicative inverse. That is 1 plus A equals to, taking the identity inverse property, 1 plus A equals to B plus A equals to C plus A. How we will write A inverse equals to 1 instead of A inverse, B plus A into C plus A. 1 plus A equals to, using the multiplication property, BC plus A. That implies, now X plus A equals to Y plus A, we are writing X minus Y belongs to A. Now this property we are using here. That implies 1 minus BC belongs to A and A is subset to B. Means we can write 1 minus BC belongs to B. Since B is an ideal, so we can write belongs to A as belongs to B. Consider 1 equals to and add and subtract with BC. Now 1 plus BC you write in brackets minus BC, and you compare with this 1 minus BC belongs to B. It is in the form of like that, so we can write belongs to B, means 1 belongs to B. By taking 1 belongs to R, you got 1 belongs to B, so we can say R subset to B. Here B subset to R, here you got R subset to B, means we can write R equals to B, means A is a maximal ideal of R. Hence R by A is a field if and only if A is maximal. Problem: let R be a non-zero ring such that A square equals to A for all A belongs to R. We have to prove R is a commutative ring of characteristic 2. Given R is a ring and they gave the formation A square equals to A. What we have to prove? Characteristic R equals to 2. Now I am considering the element instead of A as A plus A whole square equals to, write in the given formation, A plus A whole square equals to A plus A. Now split it, A plus A whole square as A plus A into A plus A equals to A plus A. Now multiply, you will get A square plus A square plus A square plus A square equals to A plus A. Now instead of wherever you have the A square, substitute with A, means A square in the place of A square as A. That is A plus A plus A plus A equals to A plus A. You add plus 0. Now you see the first right side value A plus A, you have A plus A, and you can equate A plus A equals to 0. A plus A is nothing but 2A equals to 0 for all belongs to R. Now this 2A equals to 0, you compare with the characteristic definition, nx equals to 0 means n value will be the characteristic value. Here instead of n you have 2, means we can write the characteristic of R is 2. And here we wrote for I not equals to j, and A can be written as 1 dot A and A dot 1, which does not equals to 0, means they asked you to find R is a commutative ring of characteristic R. Here it's satisfying the commutative 1 dot A equals to A dot 1. Hence we can say characteristic of a ring is 2. Next problem: find all maximal ideals in Z8, Z10, Z12 and Zn. A bit Z8 equals to, you have to write in the bracket from 0 to n minus 1 elements. Here 8 is the element, so we are writing 0 to 7 elements. What are the positive elements of 8? Are 1, 2, 4, 8, which positive which divides 8. The elements are 1, 2, 4, 8. Now for each one we have to find the generator. The ideals of Z8 are generator 1. Generator 1, how we are writing Z8 means if you multiply 1 zeros are 0, 1 ones are 1. You have to write in the generator which are less than Z8. Now 0 ones are 0, 1 ones are 1, 1 twos are 2, 1 3 multipliers of 1 which are less than the given value. Now coming to the generator 2, multipliers of 2 which are less than the given value, then you will get 0, 2, 4, 6. Coming to the generator 4, multipliers of 4 which are less than the given value, then you will get only 0, 4. Coming to the generator 8, multipliers of 8 which are less than the given value 8, then we will get only 0. Now you see generator, how we will write the maximal ideal means 0 and itself value. Here in generator 2 you have 0 and 2. In generator 4 you have 0 and 4. See here already 0 and 4 is there in the generator 2, means we can write generator 4 subset to generator 2. In the maximal ideal, A subset to B subset to R is there. If it's a subset, then we have to write A equals to B or B equals to b equals to r, but here 4 is not equals to 2 because 4 is greater than 2. So here generator 4 is not maximal, only generator 2 is maximal. Coming to the Z10, you have understood how to write the generator, only the multipliers of that particular generator which is less than the given value. Now here you see how we will write the maximal ideal means it should have 0 and itself value, and it should not be subset to anything. Now generator 2 equals to, you have 0 and itself value, and coming to the generator 5 also 0 and itself, so we can say maximal ideal. Coming to the Z12 also, after writing all the generators, generator 2 0 and itself having the elements. Coming to generator 3 also, you have 0 and 3 itself. Now coming to the generator 6, you have 0 and 6 itself, but which is there in the generator 2, and generator 6 will be subset to generator 2, but it is not equals to 6 equals to 2. So generator 6 is not a maximal ideal, only generator 2, generator 3 are maximal ideals. This Zn we can write it in our own words. How we did the problems the same way, by taking the generator t and multipliers of generator, we will form the maximal ideals. Hope you all have understood. Thank you.